All right, well, hello and good morning. Happy Wednesday. We are continuing right along discussing NumPy. So NumPy is very important. It allows for kind of fast operations, especially for the way we think about vectorized operations in R. NumPy is going to be the architecture that allows for similar types of things in Python. So we have that. Okay. Let's see. So we're gonna load this up. Import NumPy as np, and so I want to just show you a few operations as far as kind of like one of the operations is concatenating arrays, where you can kind of take two matrices or arrays if they're higher dimension, and you can kind of glue them together. All right. So here I'm creating a one-dimensional array called x, length 4, and I've got a one-dimensional array called y, also length 4. Right. And then, so we have x is 0, 1, 2, 3, and y is 100, 101, 102, 103, and these are separate one-dimensional arrays. So what you can do is you can put x and y together, and it will glue them together. Okay, so in this case, there's only one dimension along which to concatenate, because this is one dimensional and this is one dimensional. So it's just going to glue them together into a length 8. Okay, and so that's what we end up getting when you do np concatenate. Okay, np.concatenate has an axis argument, and it tells Python along which axis to do the concatenation. So by default, well, not by default, but here the axes are 0 indexed. So the first axis, basically the length, is axis 0, and so when you concatenate, you get the exact same result. Okay. Now, what if I want to stack them? Okay, what if I want to end up with a matrix that's 2 rows and 4 columns? Okay, one thing I might try is I might try to concatenate along axis 1. Okay, but it's going to tell you that you can't do that, right? And the reason why is because the shape of the dimension, the dimension of this thing is just length 4. It's not 1 by 4, but it's just length 4. Okay, it's one dimensional. So it's kind of like the idea of taking a line and stacking another line on top of it, and like you just there's no thickness to it. Okay, it makes sense to take a rectangle, and a rectangle you can kind of stack a rectangle on top, and you get either a taller rectangle, or you stack them, join them side by side, and you get a wider rectangle. But you can't do that, right? But we do have a function called vstack, and this will take one-dimensional arrays, okay, and then stack them vertically, and this will allow for that, and this will create a second dimension. So now we have a 2 by 4. Okay. The other way you can do this is you can also reshape x and y into two-dimensional arrays. And so now by doing reshape 1, 4, this is now a two-dimensional array, right? And again, the visual cue or clue that lets us see that it is two-dimensional is that we have two opening square brackets, okay? And so when you see two opening square brackets, that means it's going to be two-dimensional. And so here, I can reshape it into a two-dimensional 1 by 4, and I can stack, I can concatenate them along axis 0, okay? And so if you think about the thing 1, 2, 3, 4 here, okay? What are the dimensions? The shape is 1 by 4, okay? And so here when we do, so this is the axis. This is axis 0, and this is axis 1, okay? And so when you do concatenate here, basically, and we say concatenate along axis 0, I have, y is also going to be, so y dot shape is going to be 1, 1, 4. And so concatenating along axis 0, we're going to basically be adding the 1 and the 1, right? And so the result is going to be 2 by 4, okay? But if I say, so this is concat with axis 0, and if I concat with axis 1, okay, then we're going to take the 4 and the 4, and we'll end up with a 1, 8. Okay, does that kind of make sense as far as concatenating? Concatenating the different axes. So concatenating along axis equal 1, we're looking at the 4, and the 4 and the 4 add up to 8, so we'll end up getting a 1 by 8. All right. All right, so here I've got an x and a y as well. X matrix and y matrix, and these are both going to be 2 by 3 matrices. Okay, so if I say xm shape and ym shape, they're both 2 by 3. All right, so this time, so quiz time for you. All right, so the x shape here is 2 by 3, y shape is 2 by 3. So if I concatenate along axis 0, what is the resulting shape going to be? So x shape is 2 by 3, y shape is 2 by 3. Axis 0 refers to what? The 2 or the 3? The 2. All right, so if we're concatenating along axis 0, we're going to basically add the 2 and the 2 together, and we're going to get a 4 by 3. Okay. Oh yeah, the default is to do axis 0. Okay, here I can specify axis 0. And if I do along axis 1 points to the 3 columns. Okay, and so 3 plus 3 would add up to 6, and the result is going to be a 2 by 6. Okay, so we can kind of join them together there. You also have V stack and H stack, and you have that. Okay, if you try to do stuff where the axes don't line up, you're going to run into an error. So if I like transpose one of these things, okay, so if I transpose x, so it's a 3 by 2, then it says all of the input array dimensions except for the concatenation axis must match exactly. But along dimension 0, the array at index 0 has size 3. So xm transpose it's complaining it's saying 3 by 2, and the array at index 1 has size 2. So I mean, this is a very descriptive error that basically says this one's I'm trying to concatenate. I have a 3 here, and I'm going to have a 2 here. Okay, if I do xm transpose, right? If I do ym transpose, then this will work. Okay, and so now I have a 3 by 2 and a 3 by 2, and I'm joining them along axis 1. Okay. All right, so let's go back. We have x and y, and x is this one-dimensional array, length 4. And just like dealing with R vectors, the behaviors of these things are very similar. So I think this part will be very familiar, especially if you're coming from R and you know how R vectors work. So add 5, you're going to add 5 to all of the elements. So 5, 6, 7, 8. X plus y, you're going to do element-wise addition. So the 0 gets added to 100, 1 gets added to 101. So you get 0, 102, 104, 106. Element-wise multiplication. So 0 times 100, 1 times 101, 2 times 102. You end up getting that. Okay. You can call sum on the thing, and so basically we have the product here, and then we're adding them all up. That's equivalent mathematically to doing the dot product, okay? And so you can call np dot dot. And don't get thrown off by this np dot int64. This is just saying this is an integer and the value is 614, okay? So this is, for most intents and purposes, this is the same as just integer 614, okay? There is a subtle difference in that in Python, integers are unbounded. I don't know if you remember way back, like secondary class, I don't know. Early on, I just said like you can do something like 2 to the power of 1024, or 2 to, you know, it's just some really big number. And integers in Python are unbounded, and we'll use various memory space. In NumPy, again, for the computational efficiency, they allocate a certain amount of memory. And so NP int64 does have a maximum size, whereas regular Python integers. Yeah, question? Bracket, oh, kind of like the homework assignment where you have this? Yeah, you will run into an error. So, because np.sum is expecting, basically what it's expecting is an array. And so if you have like things embedded, so I don't think I can just so np.sum basically works for arrays. And I don't think I can convert something with brackets inside into an array. Yeah. So we would run into basically this kind of problem first, all right? And then we won't be able to do the sum. So if I try to do np.sum, it's saying, yeah, we're trying to create an array out of this, setting an array element with a sequence, and the requested array has this weird shape and an inhomogeneous part, basically saying all of these things. So yeah, so the homework problem where you have kind of these nested lists inside of each other, I recommend taking a recursive approach, okay? And so your base case will be if the element is just a number, an integer, or a float. Basically, if the element is numeric, then add that to whatever running sum is, okay? And so that's the base case. And if it's not a base case, meaning it's a list or something, then you would apply recursively to the elements within the higher level list. Okay, but anyway, going back to this, you have this. This is not the preferred usage. The @ symbol is the preferred usage for doing dot products. Dot products, you know, being do element-wise multiplication and add them together. It's just anytime. I don't know if Google search has gotten better in terms of this, but like if you're trying to search for symbols, like what does this operator mean in a language? It's often difficult, right? So let me see. Python @ meaning. Yeah, so this is kind of tough, right? So if you're reading someone else's code, yeah, it's hard to search for the meaning of certain symbolics, right? Let's see, Python @ operator. Okay, so now if we do this, now this is a decorator. So I have to say NumPy. Okay, there we go. So after a few searches, it says in NumPy, the @ operator signifies matrix multiplication, okay? And so we have that, okay? Yeah, question?
Isn't the @ symbol usually used like Gmail and stuff?
Huh?
Isn't like the @ symbol usually used like Gmail?
Yeah, the @ symbol. So the @ symbol has a weird history, okay? The modern usage is for email. It used to be for like describing prices, it'd be like potatoes at $1 per pound or something like that. I mean, I don't know how much a potato is. Okay. Yeah, so it used to be at a rate of 7 widgets at 2 pounds per widget. That was kind of the historic meaning. The modern usage is now to use as for emails, and then it just gets thrown into just if we need a character for some kind of operation, it just gets thrown in there. Okay, as far as different languages go, because most languages try to limit itself to ASCII symbols, basically the American US keyboard. And so if you need a symbol to say, hey, this is the operator, you're limited to a few things. And most of the things on your keyboard are already accounted for. Percent sign, caret is for exponentiation, and is for logical operations and stuff like that. So either you have to come up, multiple symbols together, like R, it's percent star percent for matrix multiplication. So, anyway, this is the symbol or the operator symbol for matrix multiplication in Python, or NumPy, I should say. But anyway, that's that. It's just, it's hard to search for operators when you're looking for help. Okay. Especially if you don't know the name of the operator itself. Like, I guess I know most of these names. The backtick and the tilde. Okay. All right. Anyway. Operations, add 5, addition, element-wise. Scalars just get recycled. If you have 2 matrices of the same size, you can do that, and it does element-wise things there. You also get element-wise multiplication. You can also do np.multiply, all right, and that also does element-wise multiplication. We don't have, like in linear algebra, this is not a normal thing, okay? And you have matrices in linear algebra, and you have matrix multiplication, but this is not matrix multiplication, right? Element-wise multiplication and keeping the structure of a matrix is not a. I think there's a name for it, like the Hammerhard product or something like that. It's not like a normal linear algebra thing, okay? But this is a very common thing that we do in Python, or just in computer programming and machine learning in general, is because we got to multiply a whole bunch of stuff together, but we want to keep the structure of that, okay? So dot product, np.dot is like matrix multiplication. You can do np.dot xm, the 2 things there. You can also do xm.ym, okay, the 2 matrices there. And then you can also do xm at ym, and this is probably the preferred, recommended. Okay, they all result in the same thing, but I would say using the at symbol operator as far as doing your matrix multiplication is the recommended way. Okay, let me give you your first view quiz answer, which is A as in apple, A. Okay, more basic math stuff. Okay, so addition, subtraction, multiplication, division, making the negative of. So one thing you'll notice, all of these, these are integers. When I add an integer, subtract an integer, multiply by an integer, it remains an integer. Okay, anytime you do division, even if everything remains an integer, division will always make floats. Okay, so even if I just divide by 1 and all of these are integer values, the data type is always going to be a float whenever you do division. Okay, exponentiation is star star, so x star star 2, modulo, division, and then you have I guess this is not NumPy, but that's absolute value there. Okay, we also have some trig functions in NumPy. There's trig functions in math, in the math module. Overall, if you are already using NumPy, use the NumPy functions versus the math functions in Python. So I think a few lectures ago I said, like, if you want to do the sine function, you can do import math and then do math.sine, and you can do that, and that's fine in base Python. But if you are already going to load in NumPy, which is probably going to be most of your cases, then use the NumPy functions, because the NumPy functions are engineered to be very quick and efficient when working with NumPy arrays. Okay, so if you're going to be doing computations with NumPy arrays, the NumPy function is going to be better. Okay, so anyway, we're going to create a array called theta, and this was going to be what, 0, pi over 4, pi halves, 3/4 pi, and pi. Okay, so these are the approximate decimal values. All right, so do we remember our sine values? Okay, so we get 0, what is this, root 2 over 2, 1, so on and so forth, back down to 0. And again, because it's floating point arithmetic, you don't get exactly 0. You get 10 to the negative 16. Anything on the order of, anytime you see a 10 to the negative 16, that's pretty much 0. Okay, it's almost certainly it's like an artifact. I don't want to say almost certainly. Most of the times, it's going to be an artifact of floating point arithmetic. It'll be kind of a rare situation where it's like, no, the actual value I wanted was 1.22 times 10 to the minus 16. Okay, cosine, starts out at 1. Okay, goes down to 0. Here it's 10 to the minus 17, back up to 1. Tangent. Okay, so the tangent, what, goes up to infinity. We don't actually get infinity. All right, we get 10 to the 16. Okay, so 0, 1, shooting off to infinity. This side, it ended up being on the positive side, but it could have just as easily have been on the negative side. Okay, negative 1, and then pretty much 0 there. Okay, you have log and natural log and common log. So anytime you see log, it's going to be log base e, and then if you want log base 10, it's log 10. So if we do 1, 10, 100, that's 0, 2.3, 4.6, and then 0, 1, and 2. Okay, you have the exponentiation function, e to the y. X2 is 2 to the y. And then if you want just kind of a generic raise something to some power y, you can do that. Okay, and all of these things except will accept a vector, not a vector, a NumPy array as y, and we'll keep the structure of that. Okay, doing calculations like sum and stuff, do you use numpy.sum? Okay, there is a sum function in base Python, and that works great for lists and things like that. But in general, again, if you are already working with NumPy arrays, you're going to get much faster performance using numpy.sum. Okay, because all the NumPy functions are designed to work with NumPy data structures and will work very quickly with NumPy data structures. So here I've got 0 through 99. All right, sum this gives us that, 4950. NumPy.sum gives us the same exact thing. All right, as we would expect. Here's a difference, okay? I have this commented out just because it takes a while. There's a function called timeIt, and what this will do is it will run this operation, I don't know, a bunch of times and measure how long each operation takes. So it says it took, each time I did, if I have a random array of 10,000 values and I sum them up, it took 732 microseconds. Is that right? Okay. That's with sum. And if I do numpy.sum, it runs it. I think I have them commented out. Okay. And so instead of 732 microseconds, it took 8.5 microseconds. So that's like, you know, almost 1/100th of the time. Okay. Just a little bit more than 1% of the amount of time it took. Okay. All right. You have similar things like finding the min and the max. Okay. So if what's the smallest value in our big array, what's the maximum value in our big array, we have that. Same kind of thing if you do .time it, you'll see numpy.min is going to be much, much faster than, so with the regular min, 615 microseconds, here 6.45 microseconds. So much, much faster. Okay. Here I've got some values. I just shuffled up the integers 1 through 11 in a 3x4 matrix. Okay. The regular old sum function will just give you one. Will give you column sums, which is weird. Okay. I don't know why it does that. But again, generally use numpy.sum. Numpy.sum is going to just take the entire matrix, give you one number at the end. That I think that makes a little bit more intuitive sense here. You can also numpy sum along axis equals 0. All right. So let's think about this. So we are saying take, what's the shape of this? Right? It's 3 rows, 4 columns, right? So the shape of this thing is 3 rows, 4 columns. And we're saying sum, okay, sum over axis 0. So basically when you sum over axis 0, you're going to eliminate axis 0. And so the result is going to just be length 4, okay? Right? If we say sum over so this is axis 0 and axis 1. Okay, if I say sum over axis 1, basically we're saying collapse that axis. Okay, take axis 1 and collapse it. Okay, or sum over that. So the result is going to be just length 3. Okay, same kind of idea. What's the minimum along axis 0? So anytime you do a summary function, basically a summary function takes multiple numbers and reduces it down to one number. Okay, so we're going to say reduce along axis 0. Okay, so np.min is going to find the minimum along each column. Okay, so what's the smallest value in column 1? What's the smallest value in column 2? So on and so forth. So that the result, okay, we're going to eliminate axis 0 and we'll be left with something like 4. Okay, same kind of thing. You can do standard deviations. Okay, you can do standard deviation along a certain axis. Axis 0 will collapse the column and we'll be left with 4 of them. You can calculate the mean. If I do mean along axis 1, we're going to collapse axis 1 and we'll be left with 3 values. Okay, and so we have that. Same kind of thing operates with higher dimensional arrays. Okay, so here, my shape here, I've got the shape is 2, 3, and 4, right? And so my axes are 0, 1, and 2. So quiz time. Okay, if I call sum axis 0, what is the result? What's the resulting shape going to be? If I'm saying take this thing, sum along axis 0, because it's 2 by 3 by 4. This is what it looks like. So we're going to collapse what? We're going to get rid of axis 0, which is the 2. Okay, so the result will be a 3 by 4. Okay, 3 by 4, and then the value of everything in there, because we're summing them will be 2. Okay. Okay. If I sum along axis 1, what's the resulting shape? So summing along axis 1, we're collapsing out the 3, and so the result will be 2 by 4. Okay. Yeah. And then sum along axis 2, we'll end up getting a 2 by 3. Okay. So that's how the axis argument works in any of these NumPy things. I think, let me see. Can I do axis? Can I give multiple things here? Yeah. Okay. You can also say collapse axis. You can also provide multiple arguments, right? So here the shape is 2, 3, 4. Again, 0, 1, 2. And so if I say sum across axis 0 and 1, okay, the result is going to be length 4. So this would be, I guess, sum across, I don't know, axis 0 and 1. Okay. All right. And so the result will be length 4 there. Yeah, question.
Wait, so if you have like the 2D and you're summing across like a column, is the result a 1D array, or is it like the...
Yeah, the result is 1D. Yeah. So basically you're eliminating certain dimensions, right? So here I have a 3-dimensional array that's 2 by 3 by 4, and then when you sum across one of the axes, you're eliminating one of the dimensions, and you're going to get from 3D, you're going to go down to 2D. If you have a 2D thing, okay, and you eliminate one of the dimensions, the result is 1-dimensional. Okay, so if I for any of these things, if I say dimension, oops, is it ndim? The number of dimensions is going to be 1 here, okay? Or if I do shape, the result is going to be 3, right? So perhaps if I do m.shape, okay, right now m.shape is 3 by 4, and then after you collapse axis 1, the resulting shape is going to be 3, okay? If I collapse axis 0, the resulting shape would be 4. Yeah, question? Yeah, so if you don't specify anything for axis, okay, it's going to collapse all of them, and now you don't have an array at all. You just have a number. Okay, yeah. So right, it feels a little bit strange, but if I collapse 2 of the things, we'll get a 1. So this is, I guess, 0-dimensional, right? If you collapse all 3 dimensions, you're just left with 1 number, like a point, and that would be 0-dimensional. Okay. If you collapse 2, like if you start with a 3-dimensional thing and if you collapse 2 of the dimensions, you'll be left with a 1-dimensional array. And then if you start with a 3D thing and you collapse just 1 dimension, you'll be left with a 2-dimensional matrix or array. Good. Okay. All right. The way we create missing values. So in NumPy, there's no distinction between nan and missing. So in R, these are separate things. You have nan for not a number, and then you have na for missing, and they are distinct. In NumPy, they are the same. Okay. You can create a nan value directly by calling float nan, okay? Because nan is technically a floating point number, and it's something that you get if you try to do something that's going to result in like an undefined thing. So we also have a floating point representation of infinity, okay? It's not actual infinity, it's just the idea of infinity. You can't actually do, like in regular math, you can't do like arithmetic with infinity. Like if you do infinity, I don't know. But anyway, these things result in missing. So like in the computer, if you try to do infinity divided by infinity, you get not a number or missing value unknown, and y minus y. Infinity minus infinity also results in nan. Okay. What happens if you do 7 minus infinity? You'll get negative infinity. 4 divided by infinity will give you 0. Okay. Here, remember x is nan. Okay, so x is not a number. So if you try to do sum with not a number, okay, you're going to get, just like in R, if you have a vector with a missing value, you're going to get missing. Okay, and so if you have nan along with added unto other things, you're going to get nan. Okay, so what do you do if you want to ignore? If you want to ignore nan, then there is the nan sum. Okay, this is kind of, so in R we have na.rm equals true if you want to ignore missing values, and NumPy you have the similar thing where you just say ignore missing values and you call nan sum. Okay, and so now it'll say the sum of missing and 2 if we ignore the missing values is just 2. Okay, what's the mean? If I have missing 2, 3, mean, and mean, or I'm sorry, missing 2, 3, missing, the mean of the known values is going to be 2.5. Okay, and then so basically all of these summary functions, such as sum, product, mean, standard deviation, etc., you have the nan safe version of these things, which is you just throw in nan in there, right? So and NumPy nan sum, nan prod, nan mean, so on and so forth. Okay. The another is okay, let me give you the second view quiz answer, which is the letter A. A as an apple. Second view quiz answer is A as an apple. Okay, so we can broadcast values. All right, broadcast is kind of like the idea of like recycling values in R. Python does some, or NumPy does some interesting things though. Okay. So anyway, here's A and B. These are one-dimensional arrays. We can add them together. We get a one-dimensional array. If you try to take a one-dimensional array of length 3 and a one-dimensional array of length 2, NumPy is going to complain and say these dimensions aren't compatible. Okay, because I've got a length 3 and a length 2. I'm not able to put them together. Okay. All right. Here I've got a length 3, and then I have a matrix that's 3 by 3. Right. What's going to happen if I do E plus A? Okay. What it's going to do is it's going to broadcast 1, 2, 3 across this array. So it'll add 1, 2, 3 to the first row, 1, 2, 3 to the next row, 1, 2, 3 to the next row. Okay. So we get 2, 3, 4, 2, 3, 4, 2, 3, 4. So this is a one-dimensional array, and so by default it goes across the rows. If you want it to go down the columns, so if you want 1, 2, 3 added down the column, 1, 2, 3 down this column, and 1, 2, 3 down this column, you have to reshape A into a two-dimensional array, okay, 3 by 1. All right, and so now if I take E and I add this reshaped version of A, now it will add 1, 2, 3 down the columns, and we get the first row will be all 2s, the second row will be all 3s, the last row will be all 4s. Okay. All right. Here is a 2 by 3 matrix. Okay. And if I do this, I can add that, and that works the same way. Adds across the rows. Okay. C is 7 and length 7 and 8. Okay. And if I say D. Python, if you try to do this, again, the default tries to do across rows. So if you say D and add 7 and 8, it's going to complain. Okay. But again, if I basically reshape this, okay, then I can broadcast it. Okay. Can I do D plus C transpose? Would that work? What do you guys think? So C is 7, 8. So I'm saying, okay, I want to transpose C and add it to this. Okay, I couldn't just do D and C directly because it's trying to do it across rows, and it says, hey, this is length 2 and this is length 3. That's not going to work. Okay, but if I say C transpose, would this work, or will I get an error? Huh? It'll, yeah, because C transpose, because C is one-dimensional, the transpose of it still is also going to be one-dimensional. Okay, so we get the same exact error that we do here. So I do have to do reshape. Okay. All right. So here's another thing. I've got E. E is 10 by 1, and then F is a one-dimensional length 10. All right, and so this part is a little bit strange, but if you do E plus F, what it's going to do is it's going to broadcast this to be 10 by 10, and it's going to broadcast this to be 10 by 10, and then add them all up. Okay, so so it looks at this and says, okay, this is 10 by 1, and this is, well, it's length 10, but you can imagine it being 1 by 10 also, because it treats it kind of like a row, and then it gets broadcast here. And then you can do this kind of stuff with multiplication as well. And this is basically your multiplication table. If you, I guess this is actually length 11, 10 by 11. I don't know, maybe you had to make one of these in 3rd grade or something, 2nd grade. Fill out your multiplication table, memorize this, and that's one operation there. Okay. You know, you can reshape things, and this is what you'll get there. Okay. The another important thing is we often use NumPy Boolean operations to create these true-false masks that we can then use to say, all right, you know, because like in the future when we're dealing with, say, pandas, and you have a data frame, you might want to say, hey, I only want to keep these rows. I want to only keep the rows where x is less than 3, or I want to keep only the rows where, I don't know, some other value is true. Okay, so here they're powered basically by NumPy things, and so here I've got a NumPy array. You do a operation that's going to result in a true/false. So here I'm doing is x less than 3. We're going to get an array of true/false values. Okay, so I get true, 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 false, 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 and then you have all of your kind of expected comparison operators: greater than or equal to, less than or equal to. Is it equal to, equals, equals? Okay, equals, equals we should only use for like integer values, and you know, you don't want to do is 0.2 plus 0.1 equal 0.3 because you get, you know, floating point weird things. So the equals, equals should only be used for like integers, maybe strings even. That's fine. Okay. And so anyway, once you have an array that results in true, false values, you can then use that to subset or mask values from the original thing. Okay. So here, if I only want to keep the values in x that are greater than 3, I create our Boolean mask of true and false values, and then I subset x based on that. Okay. And so now this is only going to keep 3, 4, and 5. Okay, so on and so forth. Here you can also call sum on any of these things. The falses become 0 and the ones become true. So this is basically count how many values are greater than or equal to 3. Mean is what proportion is true. So 50% of the values in that array are true. Okay. This is a little bit of a weird operator. Okay, but this is the negation. So true becomes false, false becomes true. You use the tilde operator, okay? Tilde will do the opposite. So true becomes false, and all of the falses become true. So which ones are equal to 3? You do not, okay? Now, be careful, okay? Because you might be like, oh, can I just do All right, well, so we do have the not equal operator, okay? The not equal operator in this case is these two things are equivalent, okay? But sometimes you just want to take the result and flip it around. You want the trues to become false and the falses to become true, okay? But if you do it just straight to x, okay, what the negation does is it basically multiplies it by -1, right? So, when that kind of makes sense, right? If you have a vector of Boolean values and you multiply it by -1, you're basically inverting trues to falses and falses to trues, kind of type of thing, okay? But here, the difference between negate x equal 3 versus negate x and check to see if that's equal to 3. Negating x is kind of like doing negatives of all of the x values, okay? And so it's actually not just that. It's not just it's doing negative and then -1. So to switch from true to false, you take the negative of the thing and then you subtract 1 from it, or I don't know, add 1, I don't know, something, or add 1 and then subtract 1 and then multiply by -1. Yeah, that's what we do. The negation operator takes the true value, subtracts 1, and then multiplies it by -1. False, which is 0, you subtract 1, you get -1, and multiply by -1 to get positive. So that's what it's doing. So it's subtracting 1 from x and then multiplying the result. No. Adding 1? I don't know what it's doing. It's doing something. Okay. But the negation operator does something, and it's not the same, right? It's not the same. Okay. Same kind of things. You get Boolean masks with matrices. So now you get a matrix of true and false values, and you can use the same kind of thing there, and you can call sum on all of those things. We also have element-wise Boolean operators. So this is different from spelling out and spelling out or, okay? So in Python, if you have an if statement, you spell out the word and, okay? If you have an if statement, you spell out the word or, because if you want to say if this and this is true, or if this or this is true, then do this, okay? But in NumPy, you have these arrays, and you might want to do what we call bitwise or element-wise and or, okay? So we're going to do true and true. I got true, true, false, false, true, false, true, false, okay? And these will all result in, wait, why is this A and B? Okay, I didn't run this, that's why. All right. So now I get an array of length 4, bitwise or an array of length 4, okay? And then you have this operator. This is exclusive or. Exclusive or is true if one is true and the other is false, and it's false if both are true, or false if both of them are false, okay? And then bitwise not is that, okay? You have any and all, and so on and so forth. Okay, let me give you your last view quiz answer. Last answer is the letter B. B as in bear. B as in bear. Huh? All right, and then there is what we call fancy indexing, and so you can kind of work through these examples, but basically, if you wanted to just say, I want index the subset down to index 0, index 1, and index 5, you can do that, okay? And then you can also say, I want to take X and I want to subset and I want to arrange them in a matrix. So index 1 goes here and index 2 goes there, and so on and so forth. And you can do all of these things. Okay, that's it. You have sort and argsort, and then sort along these things. I'll let you guys kind of just review the remaining few cells on your own time. But we'll go ahead and end here, and we'll see you. Oh, actually, Friday I'm gonna have to pre-record lecture. I've got an event to attend, so I'll send out an announcement, but we won't meet here on Friday. Okay, I'll pre-record the lecture and post it.